Can you guys confirm? Is my screen visible? Am I audible?
Yes, visible and audible.
Okay. Okay. So let us start today's session. It's already 6:08. So today's session will be mostly based on this heat flow analysis in welding. Uh, I have tried to cover both theoretical and numerical aspects of the heat flow analysis. Um, okay, during the time we'll see how it goes. Sure. So in question one, it says to match the followings. There are different kinds of welding techniques. Uh, so in different kinds of welding techniques, you have come across different kinds of heat sources are there. So if you see different kinds of welding, like there are tungsten arc welding, like shielded metal arc welding, resistance spot welding, gas welding, electron beam, laser spot. So they use different kinds of heat sources. So for different kinds of heat sources, the power distribution also will be different for different heat sources, right? So if we see gas tungsten arc welding, so this is part of a metal. What should I say? This is part of a shielded metal arc welding kind of thing. So if we see this arc welding with coated electrodes, so this is the most common welding process, right? So there, if you let us try to draw some schematic. Why not some schematic? So if you see for this shielded metal arc welding, there will be some electrode like this. There will be some electrode, and then of course it will have some coating over this electrode, coating like this, and then there will be your arc produced from this electrode. And then if you have this parent metal like this, there will be some deposited material and slag over there. So this is kind of slag inclusions will be uh, produced during melting of this parent material, right? So this is your arc, this is your electrode, and this is your coating of the electrode, and this is your parent metal, which are your which you are going to weld, right? Now this process is applicable for almost all metals and alloys, with the exception of there can be exception of course, some pure copper or pure aluminum or some low melting point material like um, aluminum also is having, of course, some low melting material. So for aluminum, the melting point is somewhere around 660. So there are magnesium or zinc which are having low melting temperature. So for low melting temperature material, this is a little bit trickier to weld with this arc welding thing. Now here, if we see this gas tungsten arc welding, so in gas tungsten arc welding, basically the arc is maintained between a non-consumable tungsten electrode and a workpiece, right? So there are non-consumable tungsten electrode for. Okay, let me draw for this one also. Mm, so if you see gas tungsten arc welding, there will be some inert gas supply from here. So let's say this is your supply gas, and then there can be some pressure regulator over here, and then let's say this is your torch handle. torch in the sense from where you are holding your electrode, right? And then you have this tungsten electrode over here with, here there will be some kind of gas nozzle provided. So this is your electrode basically. This is your electrode, and if this is your arc, and then you have this workpiece, and then this is connected to your workpiece, and this is connected to your power source, right? So that's how it looks like in terms of schematic for tungsten inert gas welding. Now here you have this non-consumable tungsten electrode, and the workpiece are kept in a protective inert gas atmosphere, and any filler metal needed is supplied externally, right? Normally if you see in tungsten inert gas welding, a DC arc is used with tungsten as the negative, tungsten as the negative pole. But this is not possible for metals such as aluminum and magnesium, as I mentioned, where the oxide layers also persists if the workpiece is used as the anode. So this layer prevents, basically, if you if you think of these oxide layers, these layers prevent the formation of this weld pool, right? And the cathode spot, this is mobile in nature. This mobile cathode spot can disperse the oxide layer, but excessive heat is generated at this tungsten electrode if this is used as the anode. So I think you have come across this DC electrode positive, DC electrode negative. So what happens in when you are connecting it to positive terminal, what happens you are connecting to negative terminal. So these are known things for you. So, and so for gas tungsten arc welding, what will be the correct match?
Non-consumable.
As I said, this will be non-consumable electrode. And then you have this submerged arc welding. So what happens in submerged arc welding? In submerged arc welding, the arc is maintained underneath uh, like a mass of fusible granular flux. So there will be some kind of flux will be there under which you are maintaining your arc, right? Uh, Let us not go into the detail or schematic. So this will take some time. Anyhow, this first the flux containing, what does it contain? This granular flux, it contains kind of different chemical compounds like calcium oxide, calcium fluoride, silica. Those are sintered to form a coarse powder, and this granular flux is then sprayed over this joint to be made, right? And here the electrode is consumable in nature, and it is fed into that flux, and a portion of this flux then melts to protect the liquid weld pool. So that's what the basic or principal mechanism of submerged arc welding, right? So submerged arc welding, your electrode will be consumable in nature, right? And then you have this gas welding where you have this mm, mixture of oxygen and acetylene, and then you can produce different kind of flames depending upon this oxygen and acetylene ratio, like neutral flame, oxidizing flame, carburizing flame. These are known things. So for gas welding, this will be chemical heat source you are using, right? So this is mixture of O2 plus C2H2. And then finally, what happen in electron beam welding? In electron beam welding, the heat for fusion is obtained from the kinetic energy of a dense beam of high velocity electrons. So there will be high velocity electrons. You are using the kinetic energy of that high velocity electron, and the electrons are emitted by a cathode and thereafter accelerated by some ring shaped anode, and focused by means of electromagnetic field. to finally impinge upon a very narrow area, right? So you are impinging this beam over a very narrow area. That's why the density is very high. The power density is very high for this electron beam welding, and the entire operation need to be carried out in vacuum with some pressure. And yeah, so for electron beam welding, this should be done in vacuum chamber. Otherwise there will be contamination of these oxides and air, right? So whole operation is done in vacuum chamber for electron beam welding. Any question from here? Okay, so we'll move to the next question. This also is a match of the followings. So there is something called electro slab welding, then gas cutting, then friction stir welding, and then you have this plasma spraying or coating. Just a minute. Huh. So so for electro slag welding, if you see in electro slag welding process, this is particularly suitable for welding of thick plates. It is not suitable for welding like thin or ultra thin sheets, because this can melt completely the sheet, and the property will go away if you are completely melting the sheet metal. So initially the plates to be welded are set up vertically. So uh, how should I draw a schematic of this? Okay, let us not bother about the schematic anyhow. The plates to be welded are set up vertically with some gap of about let's say 2 to 3 centimeter, and also the filler wires and the flux are kept in this gap. Whatever gap you are producing, you can fill it up with your filler wire and flux, and then this filler wires are used as the electrodes. So to start with, basically an arc is created which melts this flux, and thereafter this molten flux short circuits the arc, and heat is generated due to what should you say, ohmic heating of this slag, right? And then the slag circulates and melts the workpiece and the filler wires. So during the process, whenever the process is continuing, a little flux is added, and the whirlpool formed is covered by a layer of liquid slags, almost of constant depth. So this is the mechanism of this electro slag welding. So this is mainly suitable for thick plates, right? And then you have this gas cutting. So you know about gas welding. When you are producing gas cutting, which flame can you use for this gas cutting? So whenever in your
Oxidizing.
right, so whenever in your flame the oxygen amount will be higher, this will produce oxidizing flame, and this will produce the highest temperature. So it can cut out your workpiece. Just you can make it cut through the material with the oxidizing flame. And then I am not sure you are familiar with friction stir welding or not. So friction stir welding is a solid state welding kind of technique where if you have a workpiece like this, and you can rotate your tool, which is having some pin, of course. So this is your pin, and this is called your shoulder, and this is rotating and plunging against the workpiece. So due to rotation and plunge action, there will be some kind of axial load generated, and then due to axial load generated, there will be some kind of heat generation due to rubbing action of the tool. And due to heat generation and this load above this workpiece, there will be some severe plastic deformation happening at the workpiece surface. So you go up to some recrystallization temperature zone, and Then due to some mechanical intermixing, the joining happens. So you are not melting the material as such. The joining is happening because of some mechanical intermixing and severe plastic deformation. Okay. So for friction stir welding, this is a solid state welding technique. Now, now for plasma arc spraying and coating, are you familiar with what is transferred arc and what is non-transferred arc? Any idea? This is a little bit off topic. Anyhow, uh, so what is a plasma basically? So if you see, thermal plasma is kind of ionic form of matter. So ionic form of matter that is obtained by heating suitable gas to a very high temperature. So plasma consists of excited ions. So the ions are very much excited of gaseous atoms and free electrons. So there are ions which are of course excited in nature, and you have free electrons. So your plasma consists of these two things. And what happens? This localized temperature of plasma can reach you cannot imagine some 30,000 degrees C or even more. So this is such localized in nature that heat can go up to some 30,000 degrees C. That's such a high temperature can virtually melt and vaporize any kind of material, regardless of its physical state, right? And an artificially created controllable jet of high temperature plasma can be utilized for several purposes, like it can be cutting, this can be machining, this can be welding, can be coating or heat treating. There can be several purpose it can be useful. So all these processes utilizes the heat of this plasma jet in different ways to fulfill the intended purpose. However, the basic requirement for such activity is like you have this constricted jet of high temperature plasma flowing at a high velocity, right? And yeah, in order to artificially generate plasma, plasma forming gas like there can be some air or hydrogen or argon gas or nitrogen. Those can be introduced into a gas chamber at some flow rate, and this gas chamber contains tungsten electrode which is connected with a negative terminal. So these are some what should I say? Uh, some equipments or principle in terms of this plasma, how you can produce this plasma. Now coming to this different kinds of arc. So in transferred arc, so there are two different kinds of arc for plasma. One is transferred arc, another is non-transferred arc. You can google it to understand in terms of images. So I'm not providing the schematic as such. This will take some time. Anyhow, in transferred arc, I will explain what happens in transferred arc and non-transferred arc. So if you see in transferred arc, the workpiece is made an integral part of this electrical circuit. Whatever your workpiece is, this is made an integral part of this electrical circuit, and therefore the positive terminal of your DC power source is connected to the workpiece, while the electrode remains connected with the negative terminal. Okay. So for transferred arc, for transferred arc, workpiece connected to the positive terminal, and electrode is connected to negative terminal, right? And I think there is no need to mention that. uh, I think there is no need to mention that workpiece must be electrically conductive. So when sufficient voltage is applied across these two terminals, a long electrical arc forms between this electrode and workpiece. What you are familiar with in arc welding, uh, that's how something happens in between those electrode and workpiece, and through but very through small nozzle opening. So okay, let me draw some figure that will be understandable at least. So let's say this is your tungsten electrode. Let's say this is your tungsten electrode. Okay. And then you have a gas chamber. You have a gas chamber. And then maybe you have some nozzle over here for cooling purpose. So this is, let's say, some copper nozzle. And you have some conductive workpiece. This is your workpiece. And then you have this plasma over here, like this. And in your power source, this is connected to your negative terminal. Negative. You have your power source, and then you have your positive terminal. You can use some circuit breaker if there is some higher amount of voltage is producing in between this power source. है ना? So here this workpiece is an integral part of this electrical circuit in transferred arc, but which is not the case of non-transferred arc. So, huh. So in transferred arc, basically, as I was saying, it is difficult to establish the arc directly between this electrode and workpiece because of higher amount of gap. So in between this electrode and workpiece, there are huge amount of gap, like 5 to 10 mm, right? And so an auxiliary arc is established between this electrode and nozzle at the beginning of the work for a very short period. Okay, and this plasma forming gas that is pumped into this gas chamber comes out through the small nozzle opening surrounding this electrode arc. So that's how it happens in plasma arc or plasma spraying, whatever we are talking with. So there is something called plasma cutting, and then there is something called plasma spraying or coating. So for cutting per se, we use this transferred arc, and for non-transferred arc, uh, for plasma spraying or coating process, people use this non-transferred arc. So Okay, should I move to the next question? We have a lot of numericals actually.
Yes.
Okay, so let us move to the next question. So it says that you have some voltage length characteristics of a DC arc, which is given as V equal to 20 plus 40L, and where I is the where L is the length of the arc in centimeter, and then the power source characteristics is approximated by a straight line. So you have this voltage uh, voltage current characteristics, which is given as V by 80 plus I by 1000 is equal to 1, and we need to determine the optimum arc length and the corresponding arc power. How can you do that? So if you want to find out the optimum arc length corresponding to a arc power, we need to somehow make the relationship of power which is a function of the arc length, right? And if you somehow find out this p as a function of arc length, then you can do simply dpdl equal to 0, the differentiation as 0, and find out what will be the length, optimum arc length. Correct? Is it right or wrong, this approach? Any response? So what is your power? Power is voltage into current, right? And you have two functions. One is v as a function of arc length, and another is voltage and current characteristics. So from these two functions, can we find out I as a function of arc length? You just equate these two voltage. So your 20 plus 40L, which is your voltage characteristics, will be equal to will be equal to 18 to 1 minus I by 1000. This is also your voltage for the same power source, right or wrong?
Yes, sir.
है ना? So what will be your I in terms of L? Can you tell me? I as a function of L from here. So for my calculation, this is coming as something like this. Just check it if it is true or not. And then if you're getting I as a function of L, you can find out power. Power is V into I, which is 20 plus 40L, that into 60 minus 40L, that into 1000 by 80. And if you are getting power as a function of arc length, you can simply do GPTL equal to 0 to find out the optimum arc length. Correct? Yes or no? Any response? Is it making any sense what I am doing now? Is there any confusion?
No, sir. Understood.
Understood now?
Yes, sir.
Okay, great. So please respond, otherwise I cannot understand. So if DPDL is if you are making DPDL as 0, so what will happen from this function? So will be some 40 into 60 minus 40L. So this is 40 into 60 minus 40L, and then minus 40 into 20 plus 40L. That is equal to 0. So from this quadratic equation, you can find out L. Okay. And whenever you are getting L, you just uh, put that L value in your power function to find out the optimum, the corresponding arc power when you are having this optimum arc length. Is the concept clear? You can work with the answer part later also. I hope you got the concept. Is it
Yes, sir.
okay? We'll move to the next question then. This is some question from this resistance spot welding, and and I think I have already discussed in my first lecture for resistance spot welding what will be the heat flux. So you know that Q equal to I square RT for a resistance spot welding, right? Now in your resistance spot welding operation, you are using it to join some steel thin sheets, assuming complete melting. So we are assuming complete melting. There is no melting efficiency as such, and you're considering formation of a cylindrical shaped nugget, and we need to evaluate the portion of heat generated used to form this nugget. You have some values given as sheet thickness, nugget dia, weld time, energy required for melting, and then you have this current and resistance also. So how can you do that? So what do you know? Let's say portion of heat used will be equal to heat required to melt, that divided by heat generated during welding. That's the efficiency, right? Now you have this value as you have this value of energy required for melting. So Sorry, this should be per volume. Okay. So if you have this energy required for melting as 35 joule per mm cube, what should be the total heat required for melting? You have this cylindrical shaped nugget for which the dia is 6 mm, 5 by 4 into 6 square, that into you have your sheet thickness 2. So this is your total heat required for melting. And what will be the heat generated during welding? That will be simply I square RT. So you have this current, you have this resistance, and you also have this welding time. 15,000 square into 0.0002 into 0.15, right? That's how we can evaluate the portion of heat. That's how we can evaluate this portion of heat which has been used to join the workpiece. Any question?
And there are two sheets. So
Mm-hmm.
there are two sheets, right? It has got welded.
Uh, we have two sheets.
So the nugget, the length of the nugget, shouldn't it be 4 and
Acha. Yes. Yes. So if this is two sheets, if this is nugget, yes, you are correct. You should consider the total thickness. Good. That was a mistake. Yeah. Is it right now?
yes, sir.
Okay. Moving to next question then. You can, I think you can work on this obtaining the answers later also. So basically, by this time, you should focus on clearing the concepts more rather than getting some numerical value as such, the data as such. है ना?
Yes,
Okay. So we'll move to the next question. Here it says that an experimental investigation reveals that the optimum heat input for joining 1 mm thin steel sheets by gas tungsten arc welding process lies between this 40 to 80 joule per mm, and an operator conducts some experiments to join the same steel sheet under the following welding conditions. Uh, okay, so what you need to do is whether the condition is suitable to join the sheets or not. Whether the conditions is suitable to join the sheets or not. Here also the basic concept is same as we are discussing, like what will be the amount of heat which will be actually going into the workpiece. That would be that would be your voltage into current into the efficiency, right? Now you have this arc voltage, the process conditions what the operator is using is 10 volt, 25 amp, and you have this melting efficiency zero point 0.7. How much this is coming as 135, right? Is the calculation okay?
It's 175.
How much?
175.
175?
Yes.
175. 250 into 7. Yeah, 175. So if your total total power is coming as 175 volt ampere, and you have this um, optimum heat input which can lie in between 40 to 80, can we somehow basically convert this total power to something called heat input per unit length? Heat input per unit length, this will be what? This will be the total heat flux that divided by the welding speed, है ना? So if q is your in joule per second and velocity is your per second, so this will give me the heat input per unit length in terms of joule per correct? So what will be your heat input per unit length? This is one.
29.17.
How much?
29.17.
29.17
Yes.
joule per and for your optimum heat input for joining this is ranging from 40 to 80. So is this sufficient, or the operator needs to change in its process parameter?
Not sufficient.
So this is not sufficient. Either he needs to increase the voltage or increase the weld current somehow, that this thing gets increased, right? Understood, right? We'll move to the next question then.
Yes, sir.
So in next question, it says that you have some TIG welding process where your arc current and arc voltages are provided 50 ampere and 60 volt, and then your welding speed for case one, you have I1 as 50 ampere, V1 as 60 volt, and velocity is 150 per minute. And then in another process, you have case two where V2 is provided. It says that same arc welding voltage. So V2 is 60 volt. You have your welding speed, which is provided as 120 per minute. And then it says that heat input per unit length of the material remains same, so that the weld quality also remains same. And you need to find out the welding current for this case. If this heat input per unit length remains same, you can simply write this. Is it true?
Yes, sir.
So if this is true, you can simply 60 into 50 by 150, that equal to 60 into I don't know the current by 120. How much this is coming? 60, 60, 50 into 120 by 150, 40.
Yes, sir.
I2 is coming as 40 m. This question is simple, right? Okay. We'll move to the next question where it says in spot welding of two 1 mm thick steel sheets for which your density is provided for steel, which is carried out successfully by passing a certain amount of current for zero point 0.1 second. So your welding time is provided as 0 0.1 second. Rho is provided as 8,000 kg per meter cube. And then you have this resultant weld nugget formed is 5 mm in dia, 5 mm dia and 1.5 mm thick. This is nugget thickness and nugget dia. If latent heat of fusion is provided as 1400 kilojoule per kg, and you have this resistance provided as 200 micron, we need to determine the current. So first thing first, Q is I square RT. That we know, right? And what more we know? We know the latent heat of fusion. So latent heat basically during the phase change, right? When from solid to liquid, right now. So we can take it the heat flux to melt the material. So if this is Q is as 1400 kilojoule per kg, what will be the total heat flux? If this is in kilojoule per kg, your total heat flux would be 1400 into, this should be your mass of the nugget, right? Am I doing anything wrong? Just let me know. So your rho into volume would be how much? This is 8,000 kg per meter cube. That into pi by 4 into 5 square into 1.5. This is in millimeter cube. That should be multiplied with 10 to the power minus 9. This much of kg. This is your mass of the weld nugget. Correct?
2.35.
You're doing how much? How much?
2.35 into 10 raised to minus 4 kg.
This is my mass of the system. And then what will be the total heat flux? Uh, huh. How much will be the total heat flux?
329 joules.
329?
Joule.
329 joule?
Yes.
So if you're 329, you know the total heat flux 329 joule. It's simply I square RT. You have your R value, you have your T value, you need to find out I. 329 by 200 into 10 to the minus 6 into zero point 0.1, this much of ampere.
4.05 kilo ampere.
Okay,
Kilo ampere.
kilo amp.
Yes.
Oh, this is a huge current. Anyhow, you got the idea, right? Should I move to the next question, or any confusion is there? No. Great. Just wait for a while. Yeah, sorry for the inconvenience. Okay, we guys read the question. So it says that you have some welding of a thick steel plate where you're using some 200 amp, 10 volt, and some welding speed as provided. And based on this Rosenthal's three-dimensional equation, you need to calculate some 500 degrees C cooling rates along the x-axis of the workpiece for two different preheating temperature. Yeah, and you have provided the arc efficiency as 70% and thermal conductivity is given as 35 watt per meter degree C. Do you remember what is Rosenthal's equation in 3D? Let us not bother about let us not bother about so your Rosenthal's equation actually it says 2 pi t minus t naught. So I'm just copying the equation of Rosenthal's equation in 3D actually. Kr by q, that should be equal to exponential of minus v r minus x, that by 2 alpha. Okay. So here r is basically the radial distance from the origin, right? So r is basically rootable of that. And if you see, for a given material and a given welding condition, an isotherm T on a plane at a given x has a radius of r, right? So it's like if you have this, you are doing this welding, and then this is your welding speed like this, and somewhere here, I'm not sure, somewhere here you have this, if this is your x direction, towards x you have this radius r, and this is your y direction. So let's say this is your coordinate system here. The electrode tip should be your global coordinate system, है ना? So this is for your three-dimensional equation. Now can we do to the numerical? So as I was saying that along the x-axis of this workpiece, along this x-axis of this workpiece, y and z will be 0, and what will be x? X will be r. You need to find out along the x-axis of this workpiece. If this is true, this y z as 0, this equation you can do it in your own also. This equation will become t minus t naught pq by q by kx. These part will be 1, because you have this y equal to z equal to 0. Okay, so let us start from this equation. Along across this x-axis you have this equation, t minus t naught will be q by 2 pi kx. Now what can we do? Can we find out the temperature gradient from here? dt dx. So what will be dt dx? This will be q by 2 pi k, that into minus 1 by x square, है ना? So from here, if you see, you can write it like this. Can we write it like this? Is this part understandable or no? So from here, you just simply put the value of 1 by x from here. Is this okay for you?
Yes, sir.
Great. So if this is okay for you, So we got the value of temperature gradient, right? Not value exactly. We got as a function of T and K and those things, है ना? So if we got the temperature gradient, and what we know that dx dt is your velocity, the welding speed, right? Now, can we write down it like this? Can we write it down like this?
Yes, sir.
So this is your cooling rate, right? So you need to calculate the 500 degrees C cooling rate along the x-axis for different preheating temperature. So this is your cooling rate, yes or no?
Yes, sir.
Great. So if this is your cooling rate, we know the dTdx value from here. So your dTdx value is minus 2 pi k t minus t naught whole square, that divided by q into your velocity, right? So minus 2 pi k v t minus t naught whole square by q. This is my final expression. Now you have two different preheating temperature. You have two different T naught value basically. One is your 25 degrees C, which is your room temperature. That means for zero preheating, and then you are preheating it up to 250. So the initial temperature will be 250. Uh, can you do some calculation here? So you have this K value as 35 watt per meter degree C. You have your V velocity is 2 per second. You need to convert it in meter per second. So this is basically minus 2 pi into 35 into 2 into 10 to the minus 3 into 500 minus 1 will be your, let's say, room temperature, 500 minus 25, that divided by your q value. Q value is, you have your efficiency as 70%, that is first, that into 200 into 10. This is your case 1, where your preheating is 0. For case 2, T naught will be 250. Provide me some value of this cooling rate, dt, d capital T, d small t, for two cases. Is the concept clear? Let's say this equation is provided for you, and then tell me, is the concept clear?
Yes, sir.
Great. So why I'm telling you that to get the value of this cooling rate, uh, you'll understand after finding out the value. So for one case it will be higher, for one case it will be lower, of course, and check for which case it is higher and for which case this is lower, coming as lower.
For case 1, it is 70.88.
So I'm removing these parts. Anyhow, the video is getting recorded, no issue. So for case one, for case one, 70 point something. So let's say this is 71.
70.88.
Okay. And what will be for case two?
19.63.
Let's say this is 20. So is it clear that the cooling rate is getting reduced significantly by preheating? So
Yes, sir.
preheating is basically a common practice in welding high strength steel because it reduces the risk of this heat affected zone cracking. In if you see in multiple pass welding, the interpass temperature is equivalent to this preheat temperature in single pass welding. Okay. So if this is understood, should I move to next question? Any question, any confusion from here?
Yes,
No. Great. What does it tell about? So you have your experiment where you have your some 50 mm thick steel plate, and then your current and voltages are provided as 480 amp and 34 volt. And then it says that you have some heat losses due to convection and radiation, which is 1275 and 375. Calculate the heat source efficiency. This is very simple. Like, what do you know from heat source efficiency? If what is Q? Q is basically rate of heat transfer from heat source to the workpiece, right? What is Q nominal? Q nominal is the nominal power of this heat source, and Q weld is the welding time. So a portion of power provided by this heat source is transferred to the workpiece, and remaining portion is lost to the surrounding, right? So eta cannot be one. It is always less than one due to some convection and radiation heat losses. So you have some losses provided as 1275 and 375 calorie, and so the nominal Q will be 418 to 34. This is my nominal value of Q, correct? And what will be the Q transferred or Q actual? That will be 480 into 34. That minus you have your calorie value. So this is coming in terms of joule, right? So if you want to convert it in terms of joule, how much this should be? Some 4.2, correct? This is very simple. Like you have your Q actual value, which is actually transferring to the workpiece, subtracting this convection and radiation heat loss, and then you have your nominal value, and you find out the efficiency. There is nothing trickier as such. Okay, we'll move to the next question. So you have your heat transfer efficiency in arc welding of a plate using this current and voltage provided. So for 250 amp and 20 volt, the efficiency is 90%. And heat required to melt the material is 10 joule per mm cube. Again, the same kind of numerical. So heat required to melt the material is 10 joule per mm cube. Now, is the cross sectional area of the weld if if the cross sectional area of the weld joint is 30 mm square and travel speed is provided as 5 mm per second, we need to find out the melting efficiency. How can you find out the melting efficiency? This will be heat required for melting, that divided by heat supplied. Correct? So what is heat supplied? HS. Hmm. So this will be, is it right or wrong? You have your heat transfer efficiency as 90%. I hope this should be right. Can you guys confirm? So this V into I will be in terms of joule, area will be mm square. So this will be finally mm cube per second. Yes. How much this is coming? 250 into 20, that divided by 30 into 5, that into zero point 0.9. How much this is coming?
30.
How much?
30.
30.
Yes.
So if this is 30 and you have your heat required for melting is 10, so you can simply write down melting efficiency is 10 by 30. Is something like 33.3%. Got it?
Yes.
Great. Okay. So this is some theoretical, of course. What should be the right answer for this? Third one, great, right. So, in terms of pool shape, if you're increasing the heat input and welding speed both, the whirlpool becomes more elongated, shifting from some elliptical to teardrop shape, as discussed in the video lecture, right? So, I hope I should not draw it again. Anyhow, you can go through the video lecture once again. So, it basically shifting from elliptical to teardrop shape. And yeah, the whirlpools are like the pools are whatever there are figures. Uh, should I draw it again? You tell me, should I draw it again? It will not take much time anyhow. So if this is your first whirlpool, so it will elongate like this. What are these plus points? These are electrode tip. Okay. So in each pool, this cross indicates or plus indicates the position of the electrode tip relative to the pool. So higher the welding speed, the greater the, you can tell that length or length through width ratio becomes greater, right? So welding speed is high, length to width ratio will also increase. Correct. Which for which material the pool shape will be much more significant, whether it will be stainless steel or it can be aluminum. What property does it depend upon?
It depends on thermal
Sorry.
depends on thermal conductivity of the
Great. So it depends upon thermal conductivity. So much lower the thermal conductivity, so it will be more difficult for the whirlpool to dissipate heat and solidify, right? So pool shape will be more significant in stainless steel rather than compared to aluminum shapes. Anyhow, so is this my final question? This is the question 13 actually. Yeah. So arc welding has higher cooling rate as compared to electro slag welding. Is it true or wrong? So
true.
like for huh, this is true of course. Like for electro slag welding, if you see the arc welding will be higher cooling rate compared to electro slag welding, right? So this is temperature, this is time. Like there are different other welding techniques also, like laser beam welding, plasma arc welding, uh, as I was saying, gas tungsten, gas metal, submerged. So for laser beam, the heat source efficiency is very low because of the higher reflectivity of the metal surface, but can be significantly improved by uh, some kind of surface modification like raffining or coating of some material like this. Like so, the heat source efficiency are different for different kind of welding process, as we have been already discussed. So here for arc welding, this is having higher cooling rate compared to electro slag welding, right? This is as simple as that. And then you have this preheating of this welding process. This is true or we have already discussed depending upon this numerical thing. So preheating in the welding process helps in reducing the cooling rate.
So,
Sorry.
so
Hmm. So if you are preheating, your cooling rate should reduce. And then this we have already discussed, right? Uh, through your numerical. And then you have this under the same heat input at welding speed. Weld penetration decrease with decreasing uh, weld penetration decreases with decreasing power density of the heat source.
True.
That is also true. And then your which one will be the better heat sink, thin workpiece or thick?
Thick one will be better.
So thick workpiece acts as a better heat sink. Okay. I hope there should not be any question from here. These are some common sense questions. Is there any question?
No, sir.
Great. So this is the final one. This is the final numerical. You have your heat source, which is capable of transferring some wattage, which is 3 kilowatt, to the surface of a metal part, and then the heat impinges the surface in a circular area with intensities varying inside the circle. So the distribution is provided as follows: like 70% of the power is transferred within a circle of a circle of diameter 5 mm, and 90% transferred within a okay. So let's say this is having some concentric circle, this is having some dia of 5 mm, and this is having some dia of 12 mm. This is 5, this is 12. Here your transferred power is 70%, and here is your this is 90%. What are the power densities at different locations? That's very simple question. So you need to find out the inner circle area first. So let's say a inner is pi d square by 4. How much this is coming?
19.63.
19.6 mm square. Okay. And then it says that your heat source is capable of transferring some 3000 watt, and at this inner area, so if this is my inner area, the efficiency is 70%. So power is zero point 0.7 is zero point 0.7 into 3000. So this is coming as 2100 watt. So what would be the power density? How much is this?
106.98.
Okay, so this is roughly 107 watt per mm square. And then you need to find out the area of the outer region. So this region, so a outer will be how much? Pi into 12 square minus 5 square by 4. How much is this coming?
do we have to consider the annular circle or the
Mm-hmm.
whole circle?
Sorry.
Like, why are we considering the annular part?
So
I think we should consider the whole 12 diameter.
it says that that lies around the inner circle.
Oh, got
That's why I'm not considering the complete one.
it.
So it says that also 90% is transferred within a concentric circle of a diameter. This is not that much clear from here, but from here it says that around the inner one, so the dotted region. So the efficiencies are different at this region and at the dotted regions. Can you provide me a value for this?
93.46.
93.4 mm square. So if this area is 93.4, what will be the power in this dotted region? Power outside, let's say. So you have your heat source which is capable of transferring this much of what? 3000. And then in the inner circle, you have already used this 70% of this 3000 watt, right? Which is 2100 watt. So this is the uh, remaining capacity of transferring for the heat source, right? And then you have your efficiency of 90%, which is getting transferred into this region. Have you got this? So you have already used 2100 watt in your inner circle to heat it up. So whatever remaining portion is there, depending on that, you'll be using, or you will be heating up this outer region. So if this is 900, 810, correct na?
I think 90% is transferred in the whole circle of 12.
Sorry.
I guess like 90% of 3000 minus 1200, 2100. And then 90% is of total heat source. Right?
The distribution is as follows: 70% of the power is transferred within a circle of, and 90%. Uh, okay, if we are doing in that way, how much this is coming?
600.
How much?
600.
Okay, this is much smaller. Okay. Maybe in the numerical, this is not that much clear. Okay, let us stick to your concept. Okay, just a minute. So zero point 0.9 is your efficiency of this 3000, and then 2100 watt has been used. That's what you are talking about, right?
Yes.
So this is coming as 600 watt. Anyhow, this is
Yes.
much smaller for this outer region. So for outer region, your power density will be 600 by 93.4, whatever it is coming, watt per mm square. Okay, is this okay now?
Yes.
Anyone, any question from anything, whatever we discussed? Also, I'll finish it here. Meet again next week.
Thank you, sir.
So, if anyone is having no question, you can finish it off here.
Yes.
Great. Okay. Bye bye. Have a good day.